Hello everyone! Today we're going to show you all cool things about gravity and circular motion. Really awesome experiments. And that's basically our physics video. So get excited because we're going to use cool ways of showing you gravity and circular motion IRL and on the computer since it's not practical to do it IRL.
Using Universe Sandbox.
To say the least, so like we're gonna be already using Drive.
Well, yeah, okay. I just wanted to explain it.
Okay. So to begin, we're going to use a virtual planetary gravitation simulation called Universe Sandbox. Sandbox.
So what I said.
Available in Steam. Short money if you're interested because it's a really, really great physics simulator. So before we go into Universe Sandbox and get all with planets and gravity.
And soccer balls too.
And soccer balls and dice and all those other exciting things. We're going to just preface gravity. So, gravity is a pretty awesome force. I mean, it's one of the four fundamental forces, and it basically holds everything together. It's the reason why we're on this planet. It's the reason why life can exist. It's necessary to the rest of the forces to allow for life and other conditions to be brought about.
Yeah, and it's dependent on, like in the instance of two objects interacting with each other, like gravitationally, it's dependent on their masses and the distance between them.
Exactly. So, the problem with gravity, though, is that gravity is wicked weak. I mean, you, as a person, can overcome the force of gravity with any device or whatever just by throwing it up. You overcome it for that period of time, which is remarkable since you're going against the entire gravitational pull of the Earth.
So the formulas for the gravitational force between two masses and the electrostatic force between two charges are pretty similar. So for the gravitational force between two masses, you have the gravitational constant times the first mass times the second mass divided by the distance between them squared. And for the electrostatic force on two charges, you have a constant times Q1 times Q2 over the distance between them squared. So as you can see, those are pretty similar. But the different constants, the gravitational constant and the electrostatic constant, are vastly different. For the gravitational constant, you have 6.67 times 10 to the negative 11th, and for the electrostatic constant, you have 8.85 times 10 to the 9th.
10 to the 9th. That's a difference of almost 20 powers of 10. It's ridiculous. The strength of electrostatic force compared to the strength of gravity. Gravity is a significantly weaker force than most others, and obviously it requires a lot of mass to get just a little force. It's remarkable, like I was saying, how you can overcome gravity with such a little force. Think of how massive the Earth is, and yet we can overcome it just by jumping or walking or whatever. Now we're going to show you some demos that, despite all of this, gravity still, you can see gravity work on a really, really small scale, and it works pretty fast, believe it or not, even with small objects when they're away from outside influences. For our first video example, we're going to be using really, really small scale gravity. In this demo, you can see football or soccer ball and a bowling ball. Now, this is a very controlled area. Just about no gravitational forces in any other direction, other than the bowling ball and the football. You're not seeing them attract yet because I've got it paused, the simulation paused. Now here, the football already has a velocity, and it's orbiting the bowling ball. So here, take a look. Now, as the football is moving, it's pulling on the bowling ball, and the bowling ball had already been pulled on the football, and it hadn't been moving previously here, so it's got a bit of some motion, as you can see, projected, and it's constantly being changed by the football. Now, The only reason this orbit is staying relatively as it is because the football is in circular motion and attracted by the much more massive bowling ball. Now, if I were to, say, take the total velocity of the football to 0 meters per second, you can see how immediately the football is pulled in towards the bowling ball, and you can see the bowling ball's velocity adjust towards the football. So on even really small scale levels, you can see how gravitational forces work fairly quickly. With in less than a day, it's already moving significantly close to the bowling ball, and it's only accelerating. The biggest problem with small-scale gravity is that there are so many small-scale objects that if you've got a bunch of different little objects, such in this demo simulation, it is every single baseball, tennis ball, golf ball, everything pulls on each other to an extreme extent, and it affects the orbit of absolutely everything. It's as if you had one slightly massive sun and then absolutely massive Jupiters very, very close to one another. That's why small-scale gravity, most of the forces end up canceling each other out, or are far too minimal to feel. Welcome back. Now we see, in our second demo with the Universe Simulator, much larger scale gravity. You can see all of the major objects in the solar system orbiting the sun, obviously. How about we just destroy the sun? This is an excellent example of how centrifugal acceleration goes away and the objects just all shoot straight off into space. The sun, we really don't need anymore. It was overrated anyway. And with the aftershocks of the sun's explosion, you can see every object in the solar system has a direction that is absolutely straight. So, to link you to the centrifugal acceleration unit, you can see how large-scale objects behave very similarly to small-scale objects because the laws are universal, of course, and overall, it is much more difficult to replicate things on a larger scale and to have such comparable masses on a larger scale that are so close, and how simple orbits are overall.
Hi everyone, and welcome to the centripetal motion demo video prelude. So, a good place to start is defining centripetal motion as the movement of an object along a circular path, which can be thought of as the circumference of a circle. Examples of real-life applications of centripetal motion include the movement of a roller coaster car around a loop-de-loop and how you're pushed to the side of a car when you're going around a sharp turn. Similarly, gravitational centripetal motion is the phenomenon of a body being held in centripetal motion by the gravity of another object. The best example of gravitational centripetal motion is the movement of celestial bodies in orbit, of course. That just makes sense, and we demoed that in our previous demonstration with the Universe Sandbox simulation. In this demo, we will illustrate how the velocity of an object is affected by the length of the radius from it to the source of the force, the centripetal force. So the chord, in this case, will be the radius of the circle formed by the centripetal motion of the object, so the path it follows, which is circular. According to the formula, the centripetal force equals mv squared over the length of the radius. This shows that the decreasing radius will cause the velocity to increase if the centripetal force is constant. Of course, in a real-life demo where you're just swinging a bunch of CDs around on a rope, you're not going to get constant centripetal force. But, you know, you can imagine. In the second part of the centripetal motion demo, we will show how an object moving along a circular path will shoot out in a straight line when centripetal force and acceleration cease in the system. This is explained by Newton's first law, which states that an object in motion tends to stay in constant straight line motion unless an outside force acts on it. Of course, in the demo, many other outside forces are acting on the stack of CDs attached to the rope, like the air resistance and gravity and, the wind. So it's not ideal, like I said before. So to tie back to the first demo on gravitation, the CDs don't go into orbit around the Earth, of course, because the momentum and velocity...
Alright, so here I'm going to demonstrate centripetal motion with a bunch of CDs on the end of a rope. So, here we go. So as you can see, as the radius increases, the velocity of the CDs in this case decreases. So a longer radius...
If force remains constant.
What?
If force remains constant.
Yes. We're assuming the force does remain constant here. In an actual situation, this is highly unlikely. Okay, so I guess now we can demonstrate the radius decreasing and see how it goes faster. So, ta-da! Alright, so here in this next demo we're going to illustrate how when an object is going around in a circle, so centripetal motion, when the centripetal acceleration ceases to exist, it will move off in a straight line. And let's just assume this is an ideal situation. Alright, so going to let it go. Let's assume that went off in a straight line.
So, to tie back to the first demo on gravitation, the CDs don't go into orbit around the Earth because their momentum and velocity, after leaving the course of the centripetal motion, so the circle they're traveling in, is clearly nowhere close to escape velocity for Earth, which is 17,500 miles per hour. Basically, this is the speed of a projectile must achieve when launched to sufficiently counteract Earth's gravitational attraction to enter orbit, and then if the velocity is more than escape velocity, that would exit orbit but be, slightly deflected by the Earth's gravitation, of course. And that if it's less than that, you just get regular old projectile motion where, it goes up and then comes down. Yeah, so that was pretty much what happened with the CDs in reality, but we kind of cut that out of the video because it should be in a straight line, but in real life it couldn't be, so pretty cool.
Hello again. I hope you all had a blast watching these videos. We had tons of fun making them. It was a great time, and I hope you all learned a bit about gravitation and circular motion through the demos and experiments that we did. Have a great day! And be sure to check out the bloopers after the video. Or blooper.
Started?
Yeah.
Gravity doesn't work like that! Yeah, what he said.